All right, so let's start a new chapter. Today you are going to learn about electric potential, and it's chapter 17 of your textbook. Okay. All right, so before I'm going to talk about potential, let me talk about electric potential energy. Okay. And remember that in physics 1, you learn about gravitational potential energy and elastic potential energy. Okay, so the electric potential energy has some similarity with the gravitational potential energy. Okay, so let me first talk about electric potential energy and then compare it with, first let me talk with the gravitational potential energy and then go to the electric potential energy and electric potential. Okay. So here in the right hand side, you see a diagram. So there are two diagrams. One, the left hand side one is for electric potential energy and right hand side is for gravitational potential energy. Okay, so first let's talk about the gravitational potential energy. Okay, so as you know, as you learn in physics 1, that gravitational acceleration or gravitational field, we can say, is always downward, right? So I mean, that's because when you drop something, it goes downward. Okay, why it goes downward? Because earth gravitational field pull it downward. Okay, so this is the direction of the gravitational field or the gravitational acceleration. Okay, so always downward. Now let's say if we have an object somewhere here at position A, okay, then the gravitational potential energy at this point will be mgd, right? That is the gravitational potential energy at A. So when you release it, okay, so when you drop it, it goes downward. Okay, and at position B, if it is the ground, then the gravitational potential energy will be 0, right? Because here the height is equal to 0. Okay, so what is the potential energy between A and B? I mean, what is the difference in potential energy? Delta PE. So delta PE will be the final potential energy, which is at B, and minus the initial potential energy, which is at A. Okay, and you see that it is 0 minus mgd, and that is equal to minus mgd. Okay, so the change in potential energy when you drop an object from A is minus mgd. Okay, now what is the work done by the gravity? Okay, so you know that W is the work done, and the definition of the work done is F. So here, let me call it Fg because I want to know what is the work done by the gravity. So Fg is the gravitational force or the weight, and then D, and then cosine theta, right? So when we have an object here, the gravitational force or the weight is Fg, and that is equal to mg, right? And when you drop it, it goes downward, right? So the displacement is also in this direction. The direction of the gravitational force is downward, and when you drop it, the displacement direction is also downward. So here, if you substitute Fg equal to mg, and d is d, and cosine theta will be then 0 degree, right? Because both direction, force and the displacement, are in the same direction. So what you see here, because cosine 0 degrees 1, so W, the work done by the gravitational force, is mgd. Okay, so you see that there is a relationship between the work done by the gravity and the change in the potential energy. Okay, so you see that the relationship is this: the change in potential energy is equal to minus the work done by the gravity. Okay, there is a minus sign. Okay, So although I derived it for the gravitational potential energy or gravitational force, okay, this is in general true for any conservative force. Okay, so by conservative force, I mean the gravitational force or the elastic force, or here the electric force, right? In last chapter, remember that we learned about electric force and the relationship between the electric force and the electric field was something like this, right? F equal to Q0 E, where F is the force, electric force, and E is the electric field. Okay, and here E is very similar to the gravitational acceleration. Okay, so now let me let me compare it um, with the electric force or electric field. Okay, so here you see that the gravitational field's direction is always downward. Okay, and in analogy to this picture, in analogy to the right picture, I draw here the electric field downward, right? But it doesn't mean that electric field is always downward. Electric field can be downward or any direction. Okay, so I'm here I just to compare with the gravitational field, I use the same direction. Okay, so it doesn't mean that the electric field is always downward, right? Electric field can be in any direction. It could be in this direction, it could be in this direction, depending on the orientation of the charges. Okay, all right, so let's say we have we have an electric field, this electric field. Okay, and if we have a positive test charge here at point A, and if we release it, we will see that similar to the gravitational potential or potential energy, it will automatically go in this direction, in the direction of the electric field. Okay, and very similarly, you can show that the change in potential energy, change in electric potential energy is equal to minus the work done by the electric field. Okay, so in the next slide, I'm going to show in details. Okay, let's go to the next slide. Okay, so here you see that in the right hand side, we have a picture. Okay, and we have a two parallel plate. One is two parallel conducting plate, one is positively charged, another is negatively charged. Okay, and in the last chapter you already learned that when we have a arrangement something like this, the electric field line will be from positive to the negative. Okay, and inside this parallel plate, the electric field lines are parallel, which means the electric fields is uniform over there. So this is the uniform electric field E. Okay, now here you see that if we have a positive charge here, okay, if we have a positive charge here, okay, so because you see that positive is close to positive will be repelled, right? You know that positive charge are repelled by positive charge and it is attracted by the negative charge. So if you just put a positive charge here, it will automatically follow this line, the line of the electric field, right? Because on the other side we have the negative charge. Okay, positive charge is attracted by the negative charge. Okay, so it is very similar to the what you see in the last slide for the gravitational um, field, right? So here you see that when you have an object here, if you drop it, it automatically follow this line, right? Similarly, here you see that whenever you have a positive charge here, it follow this line. Okay, That means here electric field basically work on the charge. Okay, now let's see what is the work done by this electric field. Okay, so let's start from the definition of the work done. Okay, W equal to FD cosine 0 degree. Again, why it is 0 degree? Because you see that the direction of force, okay, remember that force is equal to Q0E. Okay, so if the electric field direction is this one, the forces direction will also be the same. Okay, and the displacement is happening also in this direction. Okay, so the cosine theta is cosine 0 degree, and cosine 0 degree is 1. So the direction, so the work done is FD, and F is Q0E. So when you substitute it, you get W equal to Q0E, Q0ED. Okay, so the work done by the electric field is this. Okay, now as we already see that the change in potential energy is equal to the negative of the work done, then if you substitute the value of work done, you get this. Okay, so the change in potential energy equal to negative Q0 E times the D. What is the D? D is the separation here between the two plates. Okay, and again it is the displacement here, displacement of the charge. Okay, so because of this negative sign, okay, it tells us that as it is going from position A to position B, its potential energy decreases. Okay, and it is very similar to the gravitational potential energy you see in the last slide. As it is going from this position to this position, the potential energy decreases. Here you see that was mgd, and here it was 0. Okay, we cannot exactly tell whether it is 0 at this side at position B, but we can say that as it is going from A to B, the potential energy decreases. That minus sign tells you about that. Okay, so as the potential energy decreases, the kinetic energy increases, right? Because we have to keep the total energy constant. Okay, so in physics 1, you already learned about the conservation of mechanical energy, right? The sum of kinetic energy and potential energy is always constant if there is no work done by the non-conservative force. Okay, so as it is going from A to B, the kinetic energy increases. Okay, so now at this point I'm going to define the electric potential. Okay, so far what we learn is the potential energy or the electric potential energy. Okay, now it is the time to define electric potential. Okay, so what is the electric potential? Okay, so electric potential is this one. So we normally use V to represent potential. It's basically the volt. So from the later chapter, we will be using less potential but more volt, okay, or voltage. Okay, so the potential is related to the volt or voltage. Okay, so V at point A is equal to the potential energy at this point divided by the charge. Okay, test charge. Okay, and it's very similar to this equation. Okay, so when you know the force, okay, then the electric field is force per unit charge. Okay, the same thing when you know the potential energy, the potential is basically potential energy divided by the test charge. Okay, and standard international unit of electric potential is volt. Okay, so volt is the unit of electric potential, and it is a scalar quantity. Okay, and from this equation, okay, you can show that 1 volt is equal to 1 joule per coulomb. Okay, so here you see that this is joule because this is energy, and Q0 is the charge, so its unit is coulomb. So from this equation you can derive that 1 volt is equal to 1 joule per coulomb. Okay, now in chapter 6 in physics 1, you learn that potential energy is not very important quantity, because when you change the reference, then the height changes, then the potential energy changes. Okay, in one problem we see that even when we um, change the reference point, although the individual potential energy at some point are changing, but the change in potential energy, I mean delta PE, does not change. Okay, so that's why that time I mentioned that potential energy is not a very useful quantity, but the change in potential energy, or delta PE. Similarly, here the potential, I mean individual potential at any point is not an important quantity, but the potential difference. Okay, so what is the potential difference? From the same equation, you can tell that the potential difference between 2 points, let's say B and A, is equal to change in potential energy divided by the test charge. Okay, and remember that change in potential energy means final potential energy minus initial potential energy. Okay, so remember this convention. Okay, all right. Now, what is the potential energy, potential difference between 2 points? So let me talk a little bit more about that. Okay, so in the last slide, you already see that the potential difference is equal to this. Okay, so let me write down here. Okay, so VBA is equal to change in potential energy over Q0. Okay, and we already see that the change in potential energy is equal to minus W and Q0. And also we derived the equation for W, and that was Q0 ED. Okay, Q0 cancel out, so we have minus ED. Okay, so the potential difference is equal to negative ED. Okay, so sometimes this equation is called add equation, add formula. Okay, all right. Okay, so this equation relates the potential difference between 2 points A and B, the electric field, and the separation, this separation between the separation between the two plates. So for example, here separation is D. Okay, so D is the separation between two plates. Okay, so this basically the equation there, you see that the potential difference between this side and this side is equal to ED. Okay, so if I am, sometime we ignore this negative sign here for this formula. Okay, all right. So here is the electric field and this is the separation. Okay, now if I want to know what is the electric field from this equation, we can solve it, and you see that the electric field is equal to BAD. I mean VBA over D. So if I divide the potential difference by the separation, I get the electric field. Okay, so this is another equation for the electric field. Okay, and in the last chapter, you see that the unit of electric field is Newton per Coulomb. Okay, and from this equation, you see that the unit of electric field could also be volt per meter, because you see here this is volt and this is meter. So volt per meter is another unit of electric field. So one can show that Newton per Coulomb is exactly equal to the volt per meter. Okay, all right. So sometime you may see in electric field, when you solve some electric field, your unit I mean, when you solve some electric field problem in this chapter, you may see that electric field is given in volt per meter instead of Newton per coulomb. Okay, so if so, don't be surprised. Okay, all right. All right, so the next thing I want to show you here, so when you have a positive charge means always high potential. Okay, and negative charge means low potential. Okay, so here you see that this is positive charge plate and this is negative charge plate. So it is always high, I mean positive charge means high potential, negative charge means low potential. Okay, but the energy is sorry, this is wrong. So I so this is high potential, so positive charge means high potential, negative charge means low potential. Okay, okay, so here in another picture in the next slide you can also see that. So high potential is low potential means negative charge, high potential means positive charge. Okay, but potential energy is different for different charge. For example, for positive charge, high potential energy is close to the positive charge. Low potential energy, PE means potential energy, is close to the negative charge. Okay, but for the negative charge, if the test charge is negative, so here you see that this test charge is negative. So when the test charge is negative, high potential energy is close to the negative plate. Okay, so remember this convention. Okay, so always potential is high at positive charge and low at negative charge. But if the test charge is positive, then the potential energy is high close to the positive charge and low at the negative charge. If the test charge is negative, something like this diagram, then the high potential energy is close to the negative plate and low potential is somewhere here at the I mean close to the positive plate. Okay, all right, so this is another equation I derived from one of these equation, I think this and this equation, so check it. Okay, and here this table shows some potential difference. Okay, so most common one is this one. Okay, so the AA or AAA battery. Okay, the potential difference between AA and AAA battery is 1.5 volt. Okay, and it is the potential difference between the positive terminal and the negative terminal. Okay, another common one is the car battery. Car battery is about 12 volt. Okay, another common one is the household outlet. Okay, the outlet voltage is about 120 volt. Okay, in United States it's about 120 volt, and in Europe and in Asian country it is about 240 volt. Okay, so it's at the order of 100 volt, so that's why it's right, 10 to the power 2 approximately. Okay, during automobile ignition we need about 10,000 volt. Okay, high voltage power line is very high, is at the order of megavolt. Okay, and the thunder cloud to ground is about gigavolt. Okay, all right. The next thing I'm going to talk is the equipotential lines and surface. Okay, so line means when we talk about the two-dimensional case, for three-dimension it is surface, right? You already know. Now, what are the equipotential lines or surfaces? So an equipotential line, okay, so an equipotential line is a line or surface. Okay, okay, so if it is a surface, then it is a surface. If it is a line, it is a line. Okay, line is in 2 dimension, surface is in 3 dimension. Okay, so which are these? Over which the potential is constant. Okay, so to understand better, let's consider this simulation. Okay, so let's say we have a positive charge. Okay, so let's say a positive charge, and you see that the this arrow basically shows you uh, the electric field lines. Okay. Now here at several, because it is two dimension, right? So you will see at some line, the potential is always the same. Okay. So here, because this is simulation, we can easily determine it, okay, by using this tool. Okay, so let me bring it here anywhere. Okay, you bring it and click on this pencil, and it will it will draw a potential. Okay, so for example, here it will draw a potential with the magnitude of 7.959. Okay, so you see it draws a circle. Okay, so in this circle, everywhere the potential is 7.963. Okay, so this is the basically equipotential. Okay, so you see everywhere you bring it, and if it is exactly on the green line, you will see that it is 7.96. Okay, so it's probably not exactly on the green line where we put on the other side. Okay, so that's why it's little different. Okay, so now if I bring it here and try to draw another equipotential line, now it will draw a equipotential line with potential equal to 4.412 volt. Okay, so another circle. So you see that in the first circle, everywhere the equipotential, the potential were the same. In the second circle, the potential is also same, but it is different than the first circle. Okay, now for individual single positive charge or single negative charge, it's basically the circle. Okay, or in 3 dimension it is a sphere. Okay, but when we have a combination, for example, let's say we have a positive charge, okay, here, and negative charge here. Okay, so positive charge here, negative charge here. Okay, so you see that again this shows us um, the electric field line. Okay, now if I want to know what is the equipotential line, it will be little bit complicated. Okay, so close to the positive or negative charge, it is again circle, but you will see that circles are not symmetrical. Okay, so you see that it is not symmetrical. Okay, okay, so you see that for a combination it's something like this. Okay, so for a combination of positive and negative charge or a dipole, it's something like this. Okay, all right. And I mean, by using this one, you can also show many different arrangement of charges. Okay, you can find by using this tool, this equipotential tool here, you can basically determine any combination. Okay, all right, but we are basically interested on a single positive charge, single negative charge. Okay, so you already see, and here I mean, I'm also showing it for a single positive charge. In the next slide, this is a dipole. So these green lines are the equipotential lines, and the blue lines basically shows you the, I'm going to show you the electric field lines. Okay, so the equipotential lines are by the green, and the electric field lines are by the blue. Okay, and also we are interested on the parallel plates. Okay, so for parallel plates, you see that these are the electric field lines, and these okay, so here the green lines, again the equipotential lines. So this is equipotential. Um, so this is one equipotential line, another equipotential line, and this is another equipotential line. And here you see that basically they are a straight line, okay, perpendicular to the electric field lines. Okay, so here it's easy to understand that the electric field lines and the equipotential lines are perpendicular to each other, but it is always true. Okay, so here in this line, it is, in this picture, it is although difficult to understand, but um, but I mean they are perpendicular to each other always. Okay, the equipotential line and the electric field lines are perpendicular to each other. So this is the rule. Okay, so here you see that electric field lines are always perpendicular to the equipotential lines. Okay. Okay, so the surface of a conductor is a equipotential. I mean, on the surface of a conductor, we already see somewhere in the last chapter that there is no electric field on an conductor, right? Inside the conductor, there is no electric field. Okay, but here you can show that the surface of a conductor is an equipotential. Okay, so here you see that this is 100, so this is a conductor. Okay, this is a conductor. So on it, on the surface, the volt is 100 volt. On it, it is 0 volt, for example. Okay, in 3 dimension, it looks like this for a dipole. Okay, I mean, if you convert this picture in three dimension, it will be something like this. Here different color means different potential. Okay, and on equipotential line or surface, the difference in potential is equal to 0 because this and this is the same. Okay, so difference between this is equal to 0. Okay, now we know that the change in potential is equal to this. Okay, actually, okay, so VVA is equal to delta PE over Q0. Okay, and delta PE means W Q0. Okay, so in an equipotential, VVA equal to 0, right? So you can see that W is equal to 0, and this tells us if a charge is on an equipotential line or an equipotential surface, then you don't need to do any work to move this charge from one place to another place. Okay, so the work done is equal to 0. All right, now let me talk about the electron volt. So this is another unit of energy. Okay, so earlier you learned about joule in physics 1, and then in thermodynamics you learn about calorie. Okay, now here electron volt is another unit of energy. It's normally used when we deal with small particle like electron, proton, and this kind of thing. Okay, so what is the electron volt? One electron volt is the energy gained or lost by an electron moving through a potential difference of 1 volt. Okay, and again, it is not an SI unit. Okay, SI unit is always a joule. Okay, but because joule is a very large unit for electron, proton, for this kind of thing. Okay, so in many problem we use electron volt. Okay, all right, so what is the relationship between electron volt and joule? You can show by using this equation. Work done, okay, is equal to Q0 VVA, right? At some point you see already this, right? So here, I mean, you see that VVA equal to delta PE, okay, Q0, right? So delta PE is basically VVA Q0. Now, if the potential difference is 1 volt, okay, and if we have a charge which is a electron, okay, so and if I want to move this electron from um, uh, I mean in this potential difference of 1 volt, then what we get, what the change in potential energy we get is the electron volt. Okay, so this is basically electron volt. Okay, and 1 volt is 1 volt, and 1 electron charge is, if you remember, is equal to this, right? So if you multiply this with this, you get 1.60 times 10 to the power minus 19 joule. Okay, so the relationship between electron volt and joule is this. So 1 electron volt is equal to 1.60 times 10 to the power minus 19 joule. All right. Now let me talk about electric potential due to a point charge. Okay, now to derive this equation, we need to use calculus. Okay, and because many of you don't know calculus or little and maybe have little knowledge about calculus, so I'm not going to derive it. Okay, but I'm giving you the final equation. Okay, so for a point charge, let's say we have a point charge here. Okay, and let's say it is Q, and at this point, which is a distance r, okay, the potential at this point, okay, is equal to k q over r. Okay, and you see it is very similar to the electric field. For electric field, it was something like this: k q square, sorry, q over r square. Okay, okay, for electric field it was r square. For potential it is just r. So remember that, don't confuse this with this. Okay, for electric field it was r square. For potential it is r. And yeah, so because k equal to 4 pi 1 over 4 pi epsilon naught, you may also see this equation somewhere. Okay, so remember that it is different. It's very similar to the electric field. For electric field, in the denominator we have r square. Here we have only r, and because the potential is a scalar quantity, okay, for positive charge we have to use a positive sign, and for negative charge we have to use a negative sign. Okay, so when we derive numerical problem for electric field or force in the last chapter, we ignored the negative or positive sign for charges. Okay, but remember that when you calculate the potential by using this equation, it is very important that if q is positive, make sure you enter the positive value. I mean, for positive charge you don't need to be worry about the sign, but when you are calculating a potential for a negative charge, make sure you enter the negative value. Okay, so for example, if I draw this graph for positive charge, it will be this. So you see that this is in the first quadrant. So first quadrant means all values are positive. For the negative charge, you see that in this graph, it is in the fourth quadrant, right? And all numbers in the fourth quadrant are negative. Okay. I mean, you see that, um, yeah, I mean, R is negative here. Okay, basically, we are interested on R. Okay, so R is negative. I mean, V is negative because, sorry, R is not negative because it is in this quadrant and it is below a zero line. The value of V is negative, and that's because Q is negative. Okay, when Q is negative, it will be in the fourth quadrant, and if it is in the fourth quadrant, V is negative. Okay. All right, the last thing in this chapter is the capacitance. Okay, so capacitance is a device that can store energy or charge. Okay, and it is widely used in electronic circuit. So if you break a computer or open a computer or any electronic device, you may see this kind of things. Okay, so these are all different kind of capacitors. Okay, so we use to store energy or charges. Okay, and the simple configuration of a capacitor is a parallel plate capacitor, so which consists two parallel conducting plates. So here you see that this is one, this is another conducting plate separated by some distance. Okay, all right, so separated by D, for example. Okay, sometime instead of just separating by air, so here we have only air or vacuum, we use some insulator. Okay, so for example, here in this, although it is not parallel plate capacitor, here you see that between two plates there are insulator. Okay, so this insulator have some some special name, we call them dielectric. Okay, in the next slide I'm going to talk about dielectric, but for the time being, let's say that we have two plates that are separated by some distance and there is no insulator in between. Okay, okay, so the capacitor symbols are either these or these. So here you see, because we are mainly dealing with the parallel plate capacitor, you will be using this symbol, two parallel lines, to represent a capacitor. Okay, so either this one, so sometime one parallel line and one curved line, okay, to represent a capacitor. Okay, so when you draw a schematic diagram, okay, if you want to represent a capacitor, you can use these or these. Okay, now do not confuse the capacitor symbol with the battery symbol. So in next chapter we are going to learn more about battery, and for battery we use again two parallel line, but one is two or four parallel lines. Okay, but one is bigger than other. Okay, bigger means high potential, low, I mean smaller means low potential. Okay, but for parallel for capacitor they are equal. Okay, again they are parallel but they are equal. For battery they are unequal. The bigger one is for high potential or the positive terminal, lower one is for negative terminal or low potential. Okay, now what happen when you connect a battery, I mean connect a capacitor with battery? Okay, so you see that this is the real diagram and this is the schematic diagram. So here you see that we use two parallel line to represent a capacitor and two unequal line to represent a battery. Positive side, I mean the bigger line for the positive terminal, lower smaller one is for negative terminal. Okay, so when we connect them, what will happen? So when we connect them, it will charge. Okay, so let me go to here in this simulation. Okay, so here you see that we have a plate, parallel plate capacitor, and it is connected with a battery. So here you see this is the battery. Okay, so I mean on the right hand side you see that V equal to 3 volt, that means it is the battery. Okay, and there is something at the bottom, the zigzag line. For the time being, don't worry about that. We are going to learn about this in the next chapter. We called it resistor. Okay, so here I want to show you that when I close the switch, what happened here in the capacitor. Okay, so let me close the switch. Okay, and you see that the electric field line, because now they charged. Okay, so the blue plate, okay, because it is connected to the positive terminal, you see that it is charged with positive charge, and the brown plate, because it is connected to the negative terminal, it is charged with negative charge. Okay, so when you connect a battery with I mean a capacitor with the battery, the capacitor charged. Okay, so the side that is connected with the positive terminal of the battery, it is charged with positive charge, and the other side with the negative charge, and in between you see the electric field lines. Okay, electric field lines goes from the positive to the negative. Okay, now what happen if I increase the battery voltage? Okay, so let me open switch. Okay, and then increase the voltage. So now it is 3 volt. Now what happen if I increase to 5 volt? Okay, 5 volt, and then close switch. Okay, so you see when we have 5 volt, the charge on the plate are more. Okay, so you see that there is a relationship between the charge Q and the volt on the battery, applied volt. Okay, so it's basically we see with a with experiment, we see that Q is proportional to volt. More the volt, more the applied voltage, more the charge. Okay, so now if I want to write an equation, I need a proportionality constant. Here the proportionality constant is C. Okay, now do not confuse this with the Coulomb. Okay, so it's another constant here. It's not Coulomb. It's not Coulomb. Okay, so Coulomb is um, the unit of charge. Here it is a constant, so it's two different things, although same symbol we are using. But remember that one is Coulomb. Coulomb is the charge, Coulomb is the unit of charge, and here C is a constant. We call it capacitance. Okay, so it is the internal property of the capacitor. Okay, so capacitance is the internal property of the capacitor, and it is different for different capacitor. Okay, so when you go to the electronics shop to buy a capacitor, okay, you see that in its body you will see the it's written the amount of capacitance. Okay, so for example, you will see written something like this: 1 picofarad or 1 microfarad, something like this on its body. Okay, so farad, F or the farad is the standard international unit of capacitance. Okay, so farad is the capacitance. Okay, now you see that um, here in this equation we have capacitance, and also here in this equation we have a C, and this C is different than this C. Okay, and to differentiate this and this, normally the symbol, okay, for symbol we use italics. Okay, so you see that it is italics, and for this one we use just normal. Okay, so this is Coulomb. When we use it as a unit, we use just a straight. Okay, for symbol we use italic. Okay, so 1 farad is the unit of capacitance. So C, if you solve this equation for capacitance, you get CQ over V. So you see that the capacitance is equal to the charge over voltage, or volt, or the potential difference. Okay, the unit of capacitance, which is farad, is equal to, so this is Coulomb and this is volt. Okay, so that's why 1 farad is equal to 1 Coulomb per volt. And in numerical problem you may see picofarad, microfarad, nanofarad. Okay, this kind of things, this kind of number. Okay, and picofarad, if you remember, pico means 10 to the power minus 12. So when you solve some numerical problem, make sure you convert pico to 10 to the power minus 12. If you see micro, it is 10 to the power minus 6. If you see nano, it is 10 to the power minus 9. Okay, all right, so the capacitance is the property of the capacitor. Okay, it does not depend on the voltage, but it does depend on the geometry of the capacitance and the material. Okay, so for example, for a parallel plate capacitor, something like this, the capacitance C is something like this: epsilon 0. So this is the permittivity constant of the free space, which I introduced in the last chapter, and A is the cross-sectional area of a plate, and D is the separation. Okay, so here you see that the plate is rectangular. Sometimes you may see this kind of capacitor. Okay, so circular discs. shape capacitor. Okay, so whatever the shape, it doesn't matter. Remember that the area, remember that in this equation, A is the area of the plate. Okay, it could be rectangular, it could be circular. Okay, and D is the separation. Okay, so for example, here D is this, here D will be the separation. Okay, all right. Now here you see in this equation, okay, so before I go to this, talk about this equation, let me tell you that the permittivity constant, the value of permittivity constant is this. Okay, all right. Now here you see that the capacitance from this equation, you can see that capacitance can be increased, okay, if you decrease D. Okay, I mean, if you decrease the separation between the two plates. Okay, and increasing A is not a good idea, so normally we do not increase the area. I mean, we can also increase the capacitance by increasing the area, but we normally do not do that. Okay, if we need to increase the value of the capacitance, we basically decrease the separation. Smaller the separation, higher the capacitance. From this equation, you can clearly see that. Okay, now another thing we can do is inserting dielectric in between two plates. Okay, so when you insert dielectric in between two plates, its capacitance also increases, and its capacitance increases by an amount called the dielectric constant. Okay, so in this table you see that we have a list of dielectric constant for different materials. So for vacuum and for air, it is close to 1. Okay, and for example, for paper, if you insert paper, you can increase the capacitance of a capacitor by 3.7 times. Okay, if you insert glass, okay, you can increase the capacitance by 5 times. If you insert mica, okay, you can increase it by a factor of 7. Okay, all right. Okay, so let's see what is in the simulation. Okay, so so normally two way we can increase the capacitance. Okay, one way is decreasing the separation, and another way is inserting the insulator. Okay, so let me see what we have here. I think we can show it here. Yeah, so here you see, okay, so here I can show you. uh, okay, so you see that at 1.5 volt, I mean, earlier in another simulation, you already see that the charge and potential charge and the voltage are proportional to each other. So in this simulation, you can also see that. But here I want to show you that when the area is higher, so you see that when the area is higher, there are more charges. Okay, and capacitance. Okay, so here you see that when the area is higher, capacitance is higher too. Low area means low capacitance. Okay, and when the separation is small, okay, so so it looks like this is the lowest separation I can do. So then let's increase. So if I increase the separation, you will see that it decreases. So you see that. So So at 10 millimeter, so this is the capacitance, okay, the bar, okay. When I decrease it, so you see that it is increasing, okay. Now if we insert a insulator, you will see that capacitance also increases, okay. So now let's say this is the bar on the top, it says the capacitance, okay. The green line shows the capacitance, okay. Now if I insert this insulator inside this, so you see that it increases a lot, okay. The capacitance increases a lot. So the two way we can increase, one is decreasing the distance separation, and another is inserting a dielectric. So when you insert the dielectric, the capacitance is increased uh, by a factor called the dielectric constant, okay. So when you insert a dielectric constant, your capacitance will be something like this. So you already see this part, then the new capacitance with the dielectric will be something like this, okay. Sometime we write this here, you see that the permittivity is not permittivity of the free space. Here E is equal to the permittivity of the dielectric, okay, and it is equal to K times epsilon 0, okay. All right. So K times epsilon 0 is the permittivity of the dielectric material. Okay. And here you see that in this table, it also gives us the dielectric strength. Okay. So dielectric strength means the maximum electric field it can hold. Okay. So you know that when you connect a capacitor with a battery, there is a electric field in between. So here you see, here you see there. So in between the two plates, there are electric field lines, okay? And by dielectric strength, we mean the maximum electric field it can hold, okay? So if you keep increasing the voltage, at some point you will see that the capacitors break down, okay? So breaking down means it cannot hold more than that electric field, okay? So for example, for air, the electric field is this, okay. For paper, the electric field is this, okay. So this is the maximum electric field the capacitor can hold when the paper is in between two parallel plates, and so on, okay. The last thing I'm going to talk is uh, uh, the energy that that a capacitor can store, okay. So earlier at the beginning, I mentioned that capacitor can store energy or store charge. So we already talked a little bit about the charge, but now let's see what is the energy a capacitor can store. Okay, so the easy way to understand this is to start with okay, so is to start with this equation, Q equal to CV. Okay, so you already see this equation. So when a capacitor is connected with a battery, the charge on the capacitor is equal to the capacitance of the capacitor times the voltage. Okay, now if I draw this equation, okay, we'll get something like this. Q, the charge, if Q is on the vertical axis and V is on the horizontal axis, we see a graph something like this, okay. And so this is the graph for a particular capacitance, for a particular capacitor, okay. And you see that if you compare this equation and this graph, you will see that slope of this graph is equal to C, okay. And this graph is also tells us about the energy or the potential energy that a capacitor can store, okay. And what is the energy, potential energy a capacitor can store? And that is equal to the area under this graph. Under the, here graph means the straight line. Okay, and the area under this straight line is basically this area, right? And you see this is a triangle, right? So what is the area of a triangle? Area of a triangle is half base times height, right? So here base is V and height is Q. So the potential energy a capacitor can store is equal to half QV. Okay, now there are two other equation you can get from this equation. Okay, one, so another one is this. When you substitute this equation Q equal to CV here, and you get half CV square. So there is another equation. So this is one, this is another, and the third one is this, half QV. So this time you substitute V instead of Q. So V will be Q over C from this equation, right? If you solve this equation for V, it will be Q over C. So when you substitute Q over C, you get that the last equation we get is Q square over 2C. So the three equation we can use to determine the potential energy or the energy that a capacitor can store, and that are either half QV or half CV square or Q square over 2C. Now, sometime the first equation is useful if you know the Q and V. If you know if you know C and V, then the second equation is useful. And if you know Q and C, then the third equation is useful. Okay. So that's it about the chapter. In the next class, I'm going to solve some classwork problem. All right.